In this video, we'll take a look at another derivative rule, and it's called the chain rule. So our objective is to find the derivative using the chain rule, rewrite functions so that the derivative can be taken using the chain rule or one of our other rules, and then we'll take a look at an application problem. So the chain rule is one of the most powerful rules of differential calculus. It deals with composite functions and allows us to extend the rules we have so far. So a reminder of what a composite function is from algebra. So if you have a function f equal to, say, x squared, and a function g equal to 2x plus 1, the function f composed with g of x means that we take the function g, the 2x plus 1, and substitute it inside the function f. The function f is whatever the independent variable is squared. If we take f of g of x, it means substitute the entire function in for x, and we get 2x plus 1 squared. So the types of functions that we're going to deal with look like a function, such as 2x plus 1, inside of another function. In this case, it's something squared. So let's take a look at types of functions that can be differentiated without the chain rule and those that should be done with the chain rule. So without the chain rule, notice the expressions that we have. Y squared equals x squared plus 1 is a polynomial. Y equals x plus 1 is a polynomial. 3x plus 2 is a polynomial. And then y equals x plus 5 over x squared plus 2 is one that we can do with the quotient rule. Things that we need the chain rule for are if you take an expression like x squared plus 1 and then do another operator to it. For example, this is the square root of x squared plus 1. Or you take x plus 1 to the power of negative 1/2. Or notice all of these are taking the expressions on the left, putting parentheses around them, and taking them to either a power or a radical or even a negative root or a negative power or a root. So two ways to write the chain rule. We'll take a look at what the chain rule does. So for example, I'll pick one of these examples, or even two examples. If we take a look at y equals 3x plus 2 to the power of 5, think about this as a function inside of another operator function. If this were just y equals x to the 5th, we could do the power rule, and we would get y prime is equal to 5 times x to the 4th. So think about it in that same way. We are going to take the derivative of this function itself to the power of 5. So our derivative is going to be y prime equals, apply the power rule, 5 times 3x plus 2 to the power of 4, but we're not finished because what's on the inside, we're going to take the derivative of that as well. So times the derivative of the expression on the inside. In this case, the derivative of 3x plus 2 would be 3. So we end up with a derivative of 15 times 3x plus 2 to the 4th. So we can think about this in several different ways. You can think of the function as being written as y equals some function of g of x. Then when we take the derivative, we're taking the derivative of the outside function, f prime of g of x, times the derivative of the function on the inside, which is g of x, g prime of x. So we can write that a couple of ways. The first option for the chain rule is written with the di dx notation, and we think of the function on the inside as u. So we have dy du times du dx is equal to dy dx. Or option 2, to help you think about in this way, maybe it's easier to think about it as a composition of functions. If your function is f composed with g of x, then the derivative is f prime of g of x times g prime x. So this notation is probably aligns more with the notation that we've been using. So let's take a look at some examples. So notice all of the examples that we have are a parentheses around an expression, and then they are all raised to a power. So this tells you that we're going to be able to use the chain rule. So the first example, if y equals x squared plus 1 to the power of 3, then y prime derivative equals, apply the power rule to the outside function. 3 times parentheses x squared plus 1, drop the power by 1 squared. Then times the derivative of the function on the inside, the expression inside parentheses. The derivative of x squared plus 1 is 2x, and then do multiplication, simplify that expression. 3 times 2x is 6x times x squared plus 1 squared. Let's take a look at the second example that has a degree of -1, a negative power. Again, it's an expression that has an expression or to the power of, to a power, not just x to a power, but an expression. So we use the chain rule by applying the power rule to the outside function. So we multiply -1 in front. We get -4 minus x squared. Subtract 1 from the power to the -2. Then times the derivative of the expression on the inside. The derivative of 4 minus x squared using the power rule is -2x. Then simplify your expression. We have negative times the negative is a positive 2x times 4 minus x squared to the -2. All right, next example has a fractional power, 4/3. So again, it's still the same format, x squared plus 1 to the power of 4/3. So the derivative is, apply the power rule, 4/3 times x squared plus 1 to the power of 4/3 minus 1. 4/3 minus 1 is 4/3 minus 3/3, and we're left to the power of 1/3. Then times the derivative of the expression on the inside. The derivative of x squared plus 1 is 2x. Then simplify the expression, multiply 2x times 4/3. We get 8/3 x times x squared plus 1 to the power of 1/3. The next examples 4, 5, and 6, we want to rewrite the expressions first so that we have it in the right format. So this first, instead of having -4 over x plus 2 squared, rewrite so that we have y equals -4 times the expression to a power, x plus 2 to the -2. So this is the same method that we've used when we had just something like 4 over x squared. We write it as 4x to the -2. So once you rewrite it, you can apply the chain rule. So I'm just going to take a look at the next few and rewrite them. Next, y equals the cube root of x squared plus 4 squared. To rewrite that, we would have y is equal to x squared plus 4 to the power of 2/3. Then you can apply the chain rule. Number 6 is rewritten. If you have x squared plus 1 in the denominator and you want to use the chain rule, you can bring that entire expression up to the numerator by taking it to the power of -1. All right, number 7 and 8, we have to apply more than one derivative rule. So number 7, notice it's a product of x times the square root of 2x plus 3. So if I rewrite that as y is equal to x times 2x plus 3 to the power of 1/2. The first expression is x, so now I'm going to have to use the product rule. And remember that the derivative, if y is equal to f times g, then y prime is equal to f times g prime plus g times f prime. So I've got to apply the power rule, and then we're going to end up applying the chain rule at the same time. So I'm going to let f equal x, g equals 2x plus 3 to the power of 1/2, f prime is equal to 1, g prime is equal to, here's where the chain rule comes in, 1/2 times 2x plus 3 to the power of 1/2 minus 1, which is negative 1/2, times the derivative of the inside, which is 2. So I end up with g prime equals 1/2 times 2 cancel each other out, 2x plus 3 to the power of negative 1/2. So now now that I know f, f prime, g, and g prime, we can apply the product rule. So now we've got the derivative is going to equal f x, which is x, times g prime, which is 2x plus 3 to the power of negative 1/2, plus g, which is 2x plus 3 to the power of 1/2, times f prime, which is 1. So there are many ways you can simplify this algebraically. So let's see, I'm going to go ahead and rewrite this without a negative power. So that's going to be x over the square root of 2x plus 3 plus the square root of 2x plus 3. You can, over 1. You can now get a common denominator for that, so you can add those two fractions together. The common denominator is 2x plus 3, or the square root of. So we multiply each fraction by the common denominator so we can add them together. And in the first fraction, the 2x plus 3, square root of 2x plus 3 cancel each other out. And we're left with x plus square root of 2x plus 3 times the square root of 2x plus 3 is just 2x plus 3. And we end up with a derivative of 3x plus 3. All right, next example of using more than one derivative rule at the same time. Number 8, we have y is equal to this expression in parentheses squared. So the chain rule says take the power rule, which is 2 times 2x plus 1 over 3x minus 2, drop the power by 1, so that's to the power of 1, times the derivative of the inside. So I'll write that in times the derivative of 2x plus 1 over 3x minus 2. So that means I'm going to have to use the quotient rule to find the derivative of this expression. So the quotient rule, just a reminder, if y is equal to f divided by g, then y prime was equal to g f prime minus f g prime over g squared. So the derivative is going to equal the denominator, which is 3x minus 2, times the derivative of the numerator, which is 2, minus the numerator, 2x plus 1, times the derivative of the denominator, which is 3, all over the denominator squared. Simplify our expression. Multiply 3x minus 2 times 2, we get 6x minus 4. Multiply 2x plus 1 times 3 and distribute the negative. 2 times 3 is 6x with the negative. Negative 1 times 3 is minus 3. The 6x's cancel. Negative 4 plus negative 3 is negative 7 over 3x minus 2 squared. So now I can go back to the original problem and substitute that in. So now I have that y prime equals, let me give myself a little room here, y prime equals 2 times parentheses 2x plus 1 over 3x minus 2 times the derivative I just found, negative 7 over parentheses 3x minus 2 squared. Now I can do the last simplification, that's a y prime. Multiply through the numerators. I have 2 times negative 7, which is negative 14, times 2x plus 1. In the denominator, I've got 3x minus 2 times 3x minus 2 squared. So I end up with 3x minus 2 cubed. And then you can also multiply through the numerator and end up with negative, I'll put final answer down here, negative y prime negative 28x multiply negative 14 times 1 minus 14 over 3x minus 2 cubed. So now that you know all of these derivative rules, there are many different ways you might be doing derivatives in combination. Okay, let's take a look at one example word problem. We have the displacement S in centimeters of a linkage joint of a robot is given by S equals 8t minus t squared to the power of 2/3, where t is the time in seconds. Find the velocity of the joint for t equals 6.25 seconds. So remember, if displacement is given by S, then the velocity is S prime. So what we're looking for is the derivative. So S prime of this function, let me write the function down. The function S is our 8t minus t squared to the power of 2/3. So what we want to do is we want to find the derivative and then evaluate it at 6.25 seconds. So the derivative is going to equal 2/3 times 8t minus t squared to the power of 2/3 minus 1, which is negative 1/3, times the derivative of the inside. Derivative of the inside is 8 minus 2t. So I'm going to clean this up a little bit and write it because I'm going to have to plug in 6.25. Things that go in the numerator are the 2. Things that go in the denominator are the 3. We have 8t minus t squared to the power of negative 1/3. So that means that goes on the denominator as a cube root or to the power of 1/3, however you want to write it. And then in the numerator is the 8 minus 2t. So now that I've got it in a way that I can put it in the calculator, let t equal 6.25. And we end up with 2 times parentheses 8 minus 2 times 6.25 over 3 times the cube root of 8 times 6.25 minus 6.25 squared. So we're going to put that in the calculator and see what you end up with. So if I go to Desmos or a scientific calculator, might be a little bit easier to type it in there. So you want to make sure you've got your parentheses wherever you need them. I'm going to take this as 2 times 8 is 16 minus 2 times 2 is 4 times 6.25. And then I'll put parentheses around that. That's the numerator if I multiply through by 2, divided by, I'll put parentheses on the bottom. I need 3 times the cube root. So here you can choose whether to take that to the power of 1/3 or do the cube root. It really doesn't matter. So let me see if I can find the cube root function. The nth root, here it is. So 3 times the cube root of 8 times 6.25 minus 6.25 squared, and then make sure you get out of that cube root, and we've got our parenthesis ended, and then just double check and make sure you've got it typed in correctly. Everything looks pretty good, so we end up with an answer of negative 1.35. And then now remember, that's a rate. That tells us the velocity, and that's centimeters per second. Negative 1.35. Let me write that a little bit better. Negative 1.35 centimeters per second.